Okay, section 1.2, exploring the validity of conjectures. Okay, so it says keep in mind, a conjecture can be supported or disproved with further evidence. So a conjecture is never proven, remember, but you can support it. No, I found another example where it works. No, it works here too, but you can't ever assume that a conjecture will always be true. But it can be disproved. You might come up with one example where it doesn't work, and then you can never say that it always works. Okay, so you can support it or you can disprove. But if you have new evidence and you want to revise your conjecture, then revise it. Oh, okay, now I know a little more about this thing that's going on, and I'm going to change my conjecture to this. Okay, so revision is completely fine. Okay, so example number 1 in your notes here, it says, are the horizontal lines straight or curved? Make a conjecture and then check the validity of your conjecture. So the one in your book is sort of similar to these two bottom ones, but these are 4 examples I found online. Okay, so this first example with black and white, when you first glance at it, it should look like the lines are crooked. And so your conjecture here could be the lines are crooked or the lines aren't straight. Okay, but if you were to check the validity of your conjecture, how would you check if a line was straight or not? You'd use a ruler, right? So it can be as simple as getting out a ruler. We can take that ruler and we can check, are the lines straight? And it may surprise you, but the lines are straight, aren't they? They sure don't look like that when you're looking at them, but look at every single line is absolutely straight. So once you check the validity of your conjecture, and if you changed your mind and thought, okay, I first thought that they weren't straight, but now I know that they are, you can change your conjecture to something like it's an optical illusion, but the lines are straight. You can say anything like that, okay? But once you've proven that your conjecture isn't true, you need to revise it. The second example, again, it certainly looks like these lines are not straight. It looks like it's sort of, coming out, bubbling out. It looks a bit like a ball. Again, we can check, though, with a ruler. And what do you think about the lines? Are they looking straight? They don't look straight, but when you put a ruler up there, are you feeling like they are straight? So again, that black and white's sort of playing havoc with your eyes, isn't it? Okay, if we could somehow line that up, maybe you could see that they're straight. You can even turn your ruler. Let's see if this will let me turn it. Will you let me turn it here? Nope. I also wanted to check up and down. One sec. Let's get rid of that one. See if I can get a ruler that I can get up and down. There's a ruler. It's a big one. But if I can turn it to go vertical, and if you could drag it along, maybe you could see that again the lines are straight. All right, look at example 3 and 4. Okay, these lines that are going out certainly make it look like these red lines are bending. But again, if you put a ruler up there, you'd have to change your conjecture. Hopefully you can see with that ruler that those lines are actually straight. And it is a bit of an optical illusion. Okay, so remember, you can always revise your conjecture. Okay, example number 2 says make a conjecture about this pattern and how can you check the validity of your conjecture. All right, so look at the tops, the numerators. What do you notice? Okay, we have 1 over 1 plus 1 over 2 equals 3 over 2. We have 1 over 2 plus 1 over 3 equals 5 over 6. 1 over 3 plus 1 over 4 is 7 over 12. 1 over 5 plus 1 over 6 equals 11/30ths. Okay, so let's look at the pattern and that we see. So we can certainly see that the denominators, well, let's start with the numerators. Let's start with the tops. What's the pattern that we're noticing? Well, hopefully you can tell that the numerators are all 1, aren't they? So let me make little dots, okay? 1, 1, 1, 1, 1, 1, 1, 1. All the numerators are all 1. Okay, what's the pattern going on by the denominators? RS, denominators. We have a 1 and a 2. We have a 2 and a 3. We have a 3 and a 4. We have a 5 and a 6. So the denominators are consecutive numbers in a row. Consecutive number. All right, so when we have 1 over 1 plus 1 over 2, we get 3 over 2. When we have 1 over 2 plus 1 over 3, we have 5 over 6. 1 over 3 plus 1 over 4 is 7 over 12. 1 over 5 plus 5 over 6 is 11 over 30th. Okay, look at the, and then in our answer, my numerator is the sum of the denominators. Okay, we have a 1 and a 2 on the bottom, gives us a 3. We have a 2 and a 3 on the bottom, gives us a 5. 3 and 4 make 7, and the 5 and 6 make 11. So that's kind of cool. Okay, so in my answer, the numerators is the sum of the denominators. What about the denominator? What do you think the pattern is there? Okay, where did the 2 come from? The 6 come from? Can you see the pattern? It's the product of the denominators. 1 times 2, 2. 2 times 3, 6. 3 times 4, 12. 5 times 6, 30. So, what's the conjecture? Look at the patterns. So I'm going to type this out. This pen is not working very well. I'm going to type out my conjecture. What's my conjecture? Well, we could say something like, in the sum of 2 fractions with 1 in the numerator and consecutive numbers in the denominator, the numerator of the sum equals the sum of the denominators, and the denominator of the sum equals the product of the denominators. Okay, so remember what we did? That's my conclusion. Okay, so remember we had, let's see, we had a 1, for example, we had a 1 over 2 plus 1 over 3. So if we were going to add them, we would need a common denominator of 6. 2 times 3, that would become 3. 3 times 2, that would become a 2. We would end up with 5, 6. So in the sum of 2 fractions with 1 in the numerator, right here, and consecutive numbers in the denominator, 2 and 3, the numerator of the sum equals the sum of the denominators. So 2 plus 3 is 5. And the denominator of the sum equals the product of the denominators. 2 times 3, 6. Okay, so there's my conjecture. All right, let's check one more example to see if I can support my conjecture. So let's pick something not too big. 1/6 and 1/7. Okay, so the numerators are 1, the denominators are consecutive numbers. Common denominator would be 42. We would multiply that by 7, so this becomes 7. We would multiply this by 6, so the top becomes 6. So we have 13 over 42. Does that support my conjecture? The top is the sum of my denominators? Absolutely. My denominator is the product of my denominators? Absolutely again. So I could say that this supports my conjecture. Okay, so when you make a conjecture, check it. See if you can come up with one more example that supports your conjecture.